Hello and welcome back to my YouTube channel. My name is Professor Gavala, and today I'm going to be doing two examples of source-free RL circuits, where the first one tells us that if we've charged up this inductor to have a current through it of 10 amps and we disconnect the DC source charging the inductor, what is the natural response IL of t going through it, and what is the current IX going through the resistor. And then the second example is asking us if we've connected a switch where t is less than 0 and it's charged up my inductor, this 2 Henry inductor, and then we open up the switch where t is greater than 0, find the natural response IL of t for t greater or equal to 0. If you want to pause the video and try to solve this on your own and come back to the video and see if you got the correct answer, feel free to do so. So there's multiple ways to do this, but what I'm going to realize is that there's a node here. I'm going to call this Vx, and I'm going to do nodal analysis. And the baseline for nodal analysis is KCL. And I've done a video on both nodal analysis and KCL, so please feel free to check those videos out. And what I'm going to do is I'm going to label this current coming through here as I3. And I'm going to say that I3 must equal IX plus IL. So what is I3? I3 is going to be 3IL minus Vx over 4 is equals to Vx over 2 plus IL. And to be explicit, I'm saying that I3 is this voltage minus this voltage divided by this resistance. Vx or Ix is going to be the voltage across this resistor divided by this resistor. And the current across the inductor, again, is just IL. Okay. Something we want to note is that Vx from our what is an inductor video is going to be the inductance times the change in current IL over dt. And let me call this equation 1. This is, again, the voltage across this inductor. All right. So let me go ahead and plug in Vx into my equation number 2. And so I get that 3 IL minus L DIL over dt, all this times 1 over 4, is equated to 1 over 2 times L DIL over dt plus IL. Okay, so note that L is equals to 1/2. So then let me go ahead and move everything here to the right-hand side. And I'll explicitly say the terms that I'm doing. So this term here, so 0 is going to be 1/4 because it's 2 times 1/2. So DIL over dt plus IL. This term here is going to be a positive, so plus 1 over 8 because it's 1/2 times 1/4. This is DIL over dt. And then this is going to be minus 3 over 4 IL. Let me go ahead and pull out a DIL over dt. This is going to be 1/4 plus 1/8. And then this is going to be plus 1 minus 3 over 4 IL is equals to 0. I hope this equation makes sense. So then we're going to finalize this by saying that this is going to be 3 over 8 DIL over dt plus 1 over 4 IL must be equated to 0. So then if we multiply everything here by 8 over 3, I'm going to get that DIL over dt plus 2 over 3 IL must be equals to 0. So then we get our first order differential equation. And from our previous video talking about RL circuits, we know that this here is A and tau is equals to 1 over A, or tau in this case is going to be 3 over 2. So then we can go ahead and write that IL of t is equals to IL of O e to the minus t over tau. That's our natural response equation. Or simply put, IL of t is equated to 10 e to the minus 2 over 3 t. And this is in amps. And again, this is at t is greater or equals to 0. Again, without diving too much into it, realize that this equation is a decaying function. All right, so we had a current of 10 amps, and then it decays over time, right? Simply because current, again, through an inductor cannot change instantaneously. So the last thing to do is find Ix. And we know that Ix is going to be Vx over 2, right? It's the current through that 2 ohm resistor in our problem. So then this becomes 1 over 2 L DIL over dt, or simply 1/4, simply because L is 1/2. So then 1/4 D times 10 e to the minus 2 over 3t over dt. So then what do we get? We get that Ix is equals to 1/4. The derivative of 10e to the minus 2 over 3t is going to be 10 times minus 2 over 3 e to the minus 2 over 3t. So then this is equated to 5 over 3 e to the minus 2 over 3 t amps. And this is for t greater or equal to 0. So this is my Ix equation, or Ix solution. Okay, so let's go ahead and go on to the second one now. So for the second one, we have, again, two cases. So case 1, this is when t is less than 0, or when the gate is closed. We can redraw our circuit, right, to look something like this. Again, take note that the only resistors that take place is this 2 ohm resistor, the 12 ohm resistor, and the 4 ohm resistor. And the reason being is because after a long period of time of that gate being closed, this inductor acts like a closed circuit, right? So it gives the path of least resistance for the current to flow through. As a result, no current will flow through my 16 ohm resistor. Okay? So essentially the goal is to find the current through this loop here. And what we can say is that if we can find the voltage here, Vx, we can then divide it by 4 ohms to find the current. All right. So essentially Vx is equals to, I'm going to use voltage divider. And I'm going to say 12 in parallel with 4 over 12 in parallel with 4 plus 2 times 40 is Vx, times 40 volts. So again, 12 in parallel with 4, just as a refresher, is 12 times 4 over 12 plus 4 over 12 times 4 plus, divided by 12 plus 4 plus 2 times 40. This ends up being 3 over 3 plus 2 times 40 is equals to 20. And as a result, I of t, again for t less than 0, is equals to Vx over 4 ohms. So this is simply 24 over 4, which is equals to 6 amps. Right? Again, this is for t less than 0. And again, since current doesn't change instantaneously in an inductor, we can say then that IL of 0 minus is equals to IL of 0, which is equals to 6 amps. This should be I of 0. So then the next case, or case number 2, is when t is greater than 0. And essentially what our circuit looks like is, let me zoom out so we can see it, is going to be this 12 ohm resistor goes into this 4 ohm resistor, goes into this 6 ohm resistor, or 16 ohm resistor. And my inductor now acts like a battery and discharges its charged up magnetic field to the load of the circuit. All right. So essentially, this is 2 henries. And what we want to do is we want to find an IT, which is equals to I-O e to the minus t over tau, where again tau is equals to L over R equivalent. Okay. So the thing we want to find here really is R equivalent. And we notice that this is my terminal A and this is my terminal B. I'm going to look into here. I'm going to find R equivalent, which is also equal to R Thevenin. I did a video on R Thevenin, so please feel free to check that out. So we get R equivalent is equals to these two resistors added up. So 12 plus 4 in parallel with 16. So again, this is just 16 in parallel with 16. So we get 16 times 16 over 16 plus 16, which is 8 ohms. All right, so then this means then that we can then solve for tau, which is 2 Henry over 8 ohms, which is 1 over 4 seconds. And then working backwards, we can go ahead and solve for this I of t. So I of t is equals to 6 e to the minus 4t amps. And this is for t greater than 0. Again, remember, this is a decaying function again, simply because it's e to the negative 4t. And what it's telling us is that when we had our switch closed, we had a current here of 6 amps, and then it starts to decay as time goes on. If you like the video, please give it a thumbs up. If you have any questions or comments, please leave them down in the comment section below, and I'll be sure to get back to you. If you like what the YouTube channel is providing, please make sure to subscribe to the channel. It really helps the algorithm. Thank you.